Welcome back, everyone, to this fourth episode of our journey into the world of computer vision systems. In this episode as well, we will continue to analyze the general structure of a vision system, and we'll focus once again on the camera component. Specifically, today we'll look at how it's possible to form an image using a camera. And we'll get to know some parameters related to the image that allow us to understand how good the image quality is. Before we start, let's do a quick recap of what we've seen so far. The camera is made up of a sensor, which in turn is composed of a certain number of pixels. Each pixel is a light-sensitive element that is able to convert light through the photoelectric effect. The light information, meaning the photons, is converted into electrical information, meaning electrons. The number of electrons created inside each pixel is directly proportional to the number of photons that hit the pixel. The electrons present on the pixel at this point will be converted by the control electronics, which is also inside the camera, into a digital number, usually 8 bits, but not always. That will still be proportional to the number of electrons present. By transitive property, then, this 8-bit digital number will also be proportional to the number of photons that hit the camera in the first place. So how do we connect this digital number created to the brightness of the pixels within the image? For now, let's consider only black and white images, or more precisely, grayscale images, as they're called in the field. Quite simply, the number created will be proportional to the brightness of the pixel in the image, so a higher number will correspond to a brighter, lighter pixel. A lower number will correspond to a less bright, and therefore darker, pixel. If the digital number has been converted to 8 bits, I'll have 256 possible states. That's 2 to the 8th power, so from 0 to 255. At this point, the first state, so 0, means a completely dark pixel, so black. The last state, 255, will correspond to a totally bright pixel, so white. Seen this way, you understand how every image is nothing more than a matrix of numbers. The matrix will have a number of rows and columns equal to the number of rows and columns of the camera sensor. And each cell of the matrix, that is, each pixel of the sensor, will contain a number that identifies its gray level, where 0 means black and 255 means white. Let's remember that we're still talking about non-color images for now. For example, areas of the image that tend toward white will correspond to numbers that approach 255. Areas that instead tend toward black will correspond to numbers that approach 0. In between, I'll have all the possible shades of gray. This applies to every pixel in the image. In fact, if we take an image and manage to zoom in on it, in such a way that we can see the individual pixels, we can also identify each single element of this numerical matrix. In each element, there will be a value from 0 to 255, which will be proportional to the light reflected by the object being captured. And that will hit that particular pixel. At this point, we can start to define some parameters that allow us to better understand how a digital image is made. So let's start by defining one of the most well-known parameters of image resolution. Resolution represents the number of rows and columns that make up this matrix, forming the image, so it corresponds to the number of pixels that make up the camera sensor. Resolution can be expressed in two different ways, either as two numbers corresponding to the number of rows and columns in the image. So, for example, 1920 by 1080, meaning 1920 rows and 1080 columns, or as a single number, given by the product of the number of rows and the number of columns, such as 2 megapixels. And what is resolution used for? Resolution helps us understand what is the smallest recognizable detail within the image. The higher the resolution of the image, the smaller the minimum recognizable detail will be. In this example of this butterfly, we can see that with the resolution used, we can see the details of the wings very clearly. If we wanted to see much smaller details, we would need to increase the resolution of the image and, as a result, increase the resolution of the camera sensor. Now that we know what resolution is, we can define a second parameter of the image, the pixel size or pixel dimension. In fact, by knowing the image resolution R and the size of the camera sensor size, we can calculate the pixel size. The pixel size actually indicates how big a pixel is within the sensor, which is why it is usually expressed in microns. Even though it is less well known compared to image resolution, pixel size is a very important parameter because it is directly linked to the quality of the final image. In fact, having a larger pixel allows for better conversion of light information into electrical information, which leads to a higher signal-to-noise ratio. So be careful to always consider not just the resolution, but also the pixel size and therefore the sensor size. When you buy your next smartphone, pay attention when they talk about sensors with millions of megapixels, because they could still result in poor quality images. And by poor quality, I mean images that don't really match the actual scene being captured. Finally, let's wrap up by talking about aspect ratio, which is the ratio between the width and the height of the image. In fact, different types of sensors could result in final images with very different proportions. The aspect ratio obviously reflects the dimensions of the camera sensor and is in fact calculated by the ratio between the width and the height of the sensor. Aspect ratio values closer to 1 will result in more square images. The further away from 1, the more I will have rectangular images. Wider with values greater than 1, taller with values less than 1. The image resolution indicates the number of rows and columns of pixels that make up the sensor. This is important for understanding the minimum detail that can be recognized within the image. Pixel size indicates the actual size of the pixels within the sensor and is important for understanding the quality of the final image. The aspect ratio, finally, is the ratio between the horizontal and vertical dimensions of the sensor and therefore of the image. This last parameter is important for understanding what the final image will look like. In today's episode, we saw what a digital image is and how it is actually formed. We learned about some parameters related to it and saw how these could lead to different images. In the next episode, we'll talk more about images, but instead we'll focus on color and see how things change.